Yeah, hi. Good evening, everyone.
Good evening, sir.
Okay, so this is week 2 open session. I hope you have start watching the lectures of the week 2 content and you have start solving the question also. So before starting the session, if you have any specific doubt in week 2, you can mention that. So I'll cover that also. You can raise the
Sir,
hand and yeah.
I have one doubt. In the previous live session, Sir has
Huh.
told that we are not expected to memorize the algorithms, and we will. He said that we'll get it by practice. Can you please like show a demo? Like now in the week 2, there are many algorithms that has been discussed. So
I
can you
think I
please?
think in the last session I mentioned that you cannot memorize the
Ah,
implementation,
yeah.
not
But
the
how to
algorithm.
remember then? How to remember the algorithms for the exam for the OP?
Algorithm you can remember, but implementation you cannot remember. Algorithm is just an idea of logic, how we are applying the logic. So that logic is not very big, so you can easily understand that logic if you try some dry run on example by the algorithm. If you solve any some examples by the algorithm on paper and pen, then you can just remember the logic of the algorithm. Okay, just keep in your mind that what type of logic we are using in the algorithm, and after that implement that logic by your own. So this is the
So
similar thing. If
I
you are
think
solving any Python problem or any problem which you have already done in the course, so if you get the logic of to solve, then you can write the implementation for that. So same here. Here some standard algorithms are there. Algorithm means they are actually predefined at some time. So some logic is there. You need to understand that logic and then write the implementation by your own style, on own code style. Okay, so that is the basic idea of this course. So I said that in the last live session, do not try to remember or do not try to learn the implementation or code for any algorithm. Okay, that you cannot memorize,
Sir,
but
if possible,
logic
can
you
you,
can easily.
if possible,
Uh-huh.
can you show some demo, like for example, binary search or some? Can you, if
That we will
possible,
do. That we can do. Yeah, that we can do. So
you can
that we
please
will
show the
discuss.
demo,
That
sir.
we will discuss today. Huh? That we will discuss today how the
Okay,
algorithms works actually.
okay, sir.
Okay.
Thank you.
Hmm. Okay. Okay. Any other query? Any specific doubt in week 2 content? Okay. Live stream is already started. Okay. Okay. So I hope you are doing these activity questions also. So that is just we have created to understand the algorithm. So you can just deep dive into the concept with the help of these questions. Okay, so if there is no query, then I think we can go with the summary of the content, week 2 content, and we will discuss all these things. And meanwhile, if you have any doubt, you can raise the hand and you can ask in between. So let me share my screen. Yeah, I hope my screen is visible to all. Is it visible?
Yes, sir.
Okay.
Yes, sir, it's visible.
Okay, okay, fine. So as you can see, the main thing, week 2 contents are started now. So main DSA concepts. So first topic is this analysis of algorithm. Okay, so this is the main thing. Now you have already seen in the last live coding session. Sorry. Uh, any problem can be solved with different approach. Okay, so there are different logic can solve any problem. So which logic is efficient, which logic is good or fast, we can say. How we can analyze the algorithm. Okay, based off the analysis of algorithm, we can decide which algorithm or which logic is faster or taking less space. Okay, so that is a different type of metric. So this week we are discussing a little bit about this complexity analysis of the algorithms, and after that we are just discussing searching algorithm and some sorting algorithms. Okay, so three sorting algorithms we have covered in this week: selection sort, insertion sort, and merge sort. One remaining sorting algorithm which we will also discuss in the week 3 content. So these are the basic contents of the week 2. Now let's start with the main that analysis of the algorithm, this topic. Okay, because every algorithm, so in this course every algorithm which we will learn, we will analyze is also that algorithm. So what complexity of that algorithm is, okay, and we will also compare the different algorithms if we are performing the same type of task with the different logic like sorting algorithms. So we will also compare with the help of complexity. So things is, now the first understand the what is complexity. Okay, so these GitHub notes I have created where I've also added some visualization in the algorithms. You can utilize that. I've also embedded the Python tutor. You can just see the flow of code execution, how that code is working. So you can utilize this resource also, and we will also discuss the complete details. So complexity, basically what is the complexity? So complexity of an algorithm is a function basically describing the efficiency of an algorithm in terms of input data, because every algorithms what we are giving in the input, we are giving the giving some input in the terms of length, maybe some list, so that have some length. Okay, so that means we are giving some input in terms of size. Okay, so what size we are providing for the input, and we will calculate the we will analyze the algorithm based on that input. Okay, what input we are giving, and based on that how our algorithm is working. So based on the, so this is just like a function which describe the efficiency. So what type of efficiency? So we have basically two measures to check the efficiency of algorithm. First is space complexity and second is time complexity. Okay, so space complexity as per the name. Okay, so this name is clearly indicate that what we are going to measure. So space means how much space actually our algorithm is taking for some specific input. Okay, so because input may be different. Okay, so suppose if we are sorting algorithm, so our algorithms input may be some 100 elements, maybe 1,000 elements. Okay, so that input size may be changed. So for any specific input, how much space our algorithm is taking. So space means amount of memory it needs to run to the completion. So when our algorithm is running, so how much is memory it is taking to solve our problem. Okay, so that is called as a space. And generally these have two types of component. One is fixed part. Okay, fixed space. So fixed space means uh, we have some specific implementation or a specific set of instruction in our algorithm. If we are talking about the code, so we have some set of instruction. So that is actually taking the fixed size. What we have created some file and some set of sequence of instructions, and that is taking some fixed size. So that is, we can say, the size of our code file. So that is one is the fixed size, but second part is basically a variable part, because uh, as I said that if we are sorting any our sorting algorithms, so that may take some smaller input or that may take also a larger input. So we are taking some variables or list we are passing to the input. So list size may be different. So that variable part basically it is depends on the input size. Okay, so if 100 elements are coming to sort, so our memory will be required for 100 elements only. Okay, suppose if one element is stored in 4 byte, so total 400 bytes it will be required at the runtime to store that data as input. But same algorithm may work also a more element like 10,000. Okay, so that at that time this space will be increased to so we need approx 10,000 into 4 bytes in the memory to store that input size. So this is dynamic based on the input. Okay, so we can consider that like as a total space tx equal to constant memory space and dynamic or variable memory space. So this is the one things about the space complexity. Sir, record lecture. No, this is already live streamed, so that will already available on the YouTube. Okay, so this is the one part, space complexity. So now, actually, another measure is time complexity. So in this course, we will mainly focus on this time complexity measure, because space is not too much affect now these days, because in at the initial time, or many years before, so this space was also a one critical component. So like memory, that memories was very actually expensive at that time, but now this memory, or we can say this hard hardware, or this memory is actually very cheap. So this is not very important, space complexity. But time complexity is very important to increase our performance, okay, or fast increase the speed of our algorithm. So time complexity mainly, what is the time complexity? We will understand this, okay. This is very important for this course, and we will discuss this time complexity for most of approx each algorithm, okay. So the time complexity of an algorithm is the amount of computer time, okay, it needs to run to completion. So here, what is the meaning of computer time? So this is not the clock time actually, okay. uh, Here time means this is not a clock time. We are not measuring this efficiency based on the clock time. Why? Because here our algorithm may run on a different type of machines, okay, and our machine at the same time. So nowadays our processor are actually perform the multitasking, or uh, at the same time our processor perform many processes, okay. So that is not only performing our code at a time, it is also performing some internal other tasks also, okay. So we cannot calculate clock time for any code to compare the algorithms. So this here computer time is basically calculated by the total number of instruction executed by the uh, that processor, we can understand, okay. So for any specific input, how many instructions, or we can say number of instructions are executing at the runtime by our algorithms. So that count actually we are looking here for the time complexity, okay, number of instructions. So that number of instruction will remain same if we are running the same algorithm on different computer. So that is not affect. So some computer speed may be faster, or some computer may be slow in the like clock cycles. So in this case, we will calculate this time complexity in the terms of number of instructions which are executing at the running time for some specific input. Okay. So this is basically represent the computer time. Now, time complexity calculated in three type of case. So this is a input case actually. What type of input we are giving to the algorithms? So maybe same algorithms. Maybe input is we can understand that. Suppose we have some list. Okay. So we have some list. We have some random elements, okay, like a 10, 30, 3, 5, 6, 4, 9, 1. Okay. Now we are searching elements. Suppose we have this one linear search algorithm when we compare each element one by one and we figure out that our element is exist or not. Okay. And in this, so this algorithm is fixed. We are simply comparing the element from the first element to the last element, and then we are finding our element. This is exist in the list or not. So this algorithm we will apply. Now what is the possible input? What we are looking, what we are searching for this algorithm. So based on that, suppose if we are searching like 10, okay, 10 element we are searching. Our input search element is 10. So in this case, we can return the output only one comparison. So we will start our process from the first element. We will compare with this element. If our searching element is matched with the first element, we will return that this element is exist on which index. So this operation is done in one comparison. Okay, so now we can consider that this is the smallest time by our algorithm, or lowest time by our algorithm. Now same worst case. Worst case is like when our algorithm will perform the maximum time for any input. So like we are looking at element where our element is not exist in this. Okay, suppose we are looking 11. Okay, so in that case, we will compare the first element, then second element, then third, then fourth. In this way, we will compare each element till last. So, and after that, we are able to say that this element is not exist. So before that, we have compared all element. Okay, so then we are able to find that this element is not exist. So in this case, how many elements we have in the list, or that number of comparison we have performed. So suppose if we have 1 lakh element in this list and we are searching any element, so 1 lakh comparison will be done. Then we will able to return the result element is not exist. So that is the worst situation when maximum work is done by our algorithm. Okay, so average case is different. So in between these two conditions, or generally these actually calculate by what are the all possible actually searching way we have. So our element may be figure out at first position, 2 position. So each possible like each possible of input. So for suppose 10, it will take 1 comparison. For 30, it will take 2. Okay, for 3, it will take 3 comparison. So all possible input, then average of that. Okay, so that time we can consider that that is the average time or average case, where our algorithm is taking greater than best case or less than worst case. So we can just consider that as the average case. Okay, so these are the case. It is depends on the input. Our algorithm is fixed, but based on the input or type, so that our algorithm will behave differently or it will take some different time. So this is the
Sir,
case. Yes.
can you explain again best case thing?
Best case is when we are performing a linear search and our element is exist at the first place, 10. Okay, what elements we have the remaining element, and we are just looking our k element is 10, and we are searching that this 10 is exist in the list or not. Okay, then we are starting our process. We are comparing with the first element. At the first element, we found that this is matched. So only
Okay,
one
sir.
step our algorithm, only one step our algorithm will be return the output that this element is exist. So this is the smallest time our algorithm is taking for input. So this is like a best case. So these case generally we calculate the complexity. We can compare the in these case, but not for all. Mainly our focus will be on this part, worst case. Okay, worst case. Our target is to improve this worst case time. How we can reduce this worst case time. Okay, then our overall performance will be improved by the algorithm. So we will reduce this worst case time. So that is the main motive for the each algorithm. Okay, so now comes to the next part. So time complexity is not a clock time. Just understand this. This is a number of instructions which are executing at the runtime for any input, and we represent this number of input in the terms of input size. Okay, and this is a theoretical calculation. This is not very fixed calculation. Okay, we ignore some constant terms in this process, and we only takes the higher order of that relation. Okay, in the terms of input size. So this is the theoretical concept, not actually very fixed count we are counting here. We will just represent the relation of input size, and in the terms of input size, what is the total number of instructions, how the total number of instructions are growing based on the input size. So that relation we are looking here. So now next is growth rate of function.
Sir, could you
Okay,
please explain the cases again?
these 3 cases.
Yes, sir.
Okay, so as I've given the example of searching. Okay, so searching is a operation when we search any element in our existing list or array. Okay, so we have some set of elements. Suppose I think Prof have also given the example in first week. So you have suppose Aadhaar number, and your Aadhaar number is all randoms. Okay, so so suppose you have like A1, A2, A3, all these A, like, and we can say that, okay, and maybe anything are the Aadhaar number, and these are not sorted. Okay, so in that case, if we are performing any searching and we are looking for like A6, this Aadhaar number is exist in our database or not. So linear search basically perform the operation like this: start comparison from the first element. If it is matched, then it will return answer yes, it is exist at this index. Otherwise, it moves to the next element to compare. Okay, so in this way, we will compare each element one by one till the last. So this is the linear search. Okay, we are comparing our searching element with each element. Okay, from the starting position. So best case is when our searching element is matched with the first element. Okay, we are looking some Aadhaar number and which is placed at the first position of our database. So our first comparison will identify that yeah, it is exist. Okay, so only one comparison required, and after that we will stop our process. So our Aadhaar number is matched at the first location. One comparison we found the result, and we can conclude that yeah, it is exist. So this is like a best case. It is taking the minimum number of comparison. This operation is taking for this type of input. We are our algorithm is taking only minimum comparison. Worst case is when our algorithm is taking maximum work to find out the result. So like if you are searching the last element, or maybe you are just looking the element which is exist in this. So in that case, you will compare each element and you will reach at the last point. Then you will able to return the result. This element is exist either on the last position or maybe it is not exist. If it is not exist in the list. So at that time, n comparison is done. If n value is equal to 100, so that means you have done 100 comparison. Then you are able to conclude your element is exist or not. So this is the maximum work by the algorithm. Okay, average case is the in between situation. So this best case and worst case in between situation, that is represent, you can just consider that as a average case. I hope it is clear.
Yes.
Okay, so now growth rate of the function. So growth is represent how our total number of instructions are increasing in the terms of input. Okay, so the number of operations usually expressed as a function of the input. Okay, so function means, now just take this example. Okay, take this example. Suppose this is our algorithm. Okay, this is doing some task. Okay, we are so we are not focusing on what task it is doing. This is just one implementation we have. Now we figure out that what input we can consider here. So that is actually changing. That may be changed. So here n input we are taking, this n input. Okay, this may be anything for this problem. So this may be like n equal to 10, n equal to 100, n equal to 1000. So this input may be changed. But now we will figure. So we are just taking as a n value. We are not considering that as a specific. Okay, we are so this time complexity is not considered as a for a specific value. So at the place of specific terms, we use the n term. So n you can consider anything. Okay, just put the value n, any fixed to the n, and you will get the answer. So for the n terms, now consider that suppose if you are running this code. Okay, to understand better this example, just take n equal to 5. N equal to 5. Now when you are running this code for n equal to 5, now first instruction, just focus on the first instruction. How many times this first instruction will execute if n equal to 5 in your code?
One time.
One time. Okay, this s equal to 0 will execute one time always. If you are changing n equal to 100, still this is the only single instruction, and it is not coming under any loop or something. So this will only run always time, constant time. Okay, now this loop instruction. Okay, second line. This loop, just consider this as one instruction. Okay, so it is taking I in range n. So that means it is running I in range n means 0 to n minus 1. Correct? So it will read 0, then 1, then 2, then 3 till n minus 1. And then one time it will terminate. Now when this all value will complete, then it will terminate. So now if n equal to 5, how many times this loop instruction will run?
6 times, sir.
And one
5 times.
and sorry.
5 times.
So we have taken this one time for the termination condition. When we will check our now list is empty. Okay, so this list is empty now. There's no element to read. So this is the terminate condition. So I have included this one additional time for the terminate condition. Okay, because every time we are checking one value, we are reading one value from our set, and last that our all value will be complete. So this terminate situation will be there. So that is, we can also consider that as a one step. So here, if n equal to 5,
Why we are considering +1?
sorry.
So
Okay, just wait. Okay, actually, this is not very. In Python, we are not. We cannot just think about this, but see, actually, this code is written like this. So for but internally Python also work in the same way for I like I equal to 0, okay, and I is less than equal to like n minus and I plus plus. Okay, so this way loop we generally write in the C language or Java language like this. So here same, okay, this loop is also running in the same range 0 to n minus 1, but every time, so when I equal to 0, okay, then first value will be to 0. Suppose n equal to 5. So n equal to 5, and we will enter into this loop. So we will check this condition. So that means I is less than equal to 4. Okay, so this is 0. We are entering inside the loop. Then this increment happens. Okay, so then our value is increased. So it will become a 1. Now again we check condition. So 1 is less than 4. Yes, true. Okay, then we will again enter. Okay, now again increment will happen. So then it become a 2. So 2 is still less than 4. Yes, correct. Okay, so we will again enter inside the body. Then I become 3. Okay, by this increment. Then 3 is still less than 4. Yes, okay, then we will enter again and then increment 4. 4 is still less than equal to a 4. Correct. Okay, so equal sign is also there. Correct. Then again increment will happen. Okay, so again increment will happen. Then I become a 5. Then 5 is less than 4, less than equal to 4. This is the terminate condition. Okay, so we are reaching at the terminate condition when we are stopping our loop. Okay, so you can see we are taking 5, but total steps are running one more than this. So this is the terminate condition like.
Okay, sir.
Okay, so you can ignore this. As I said that we only focus on the relative part basically, and we ignore the constant later. Okay, so this one you can just leave out. Okay, but if n equal to 5, you can consider 5 plus 1 6 step. Okay, if n equal to 100, so 100 plus 1 10. So this instruction is depend on the value of n. Correct? If we will change the value, the number of times this will execute, it will also change.
Yeah, yes.
Okay, so now we are just looking this. This is a one. Okay, now this is the nested loop. Okay, I hope you understand how we write the nested loop. So for I in range n, this is the outer loop. Inside this, we are running it one nested loop. Okay, for j in range n. Now just tell me how many times second loop will run. Because so just understand this nested thing. So if if our n equal to 5, okay, so I equal to 0. When I equal to 0, we are entering inside the loop and we are running a internal loop. So internal loop will run 0 to 4, correct, for I equal to 0. So this is running 5 times. We can understand that 5 times, or 5 plus 1 times 6 times we can consider that. Okay, 1 is the terminate point. So for a single value of I, this is running 6 times. Then we will move to the outer loop. So I will become a 1. Then again j will run 0 to 5 for the true condition, and 1 is the terminate condition. Sorry, 4. So again 6 times. Okay. So I equal to 2, then j will run again full range. Okay, so 0 to,
Sir, how 6?
as I mentioned, the one I am including one terminate condition. Okay, just ignore this. If you are confusing too much in this, just ignore this. Okay. So let 5. Okay, it is clear now. So 5 steps. If n equal to 5, 5 steps. So I equal to 3, j 0 to 4. Correct. So how many times this nested loop will run?
N square.
5 times.
N square. Okay, correct. N square. Okay, and how many times this instruction which is inside the nested loop, j loop, how many times this will run?
N square or N.
Same n square time.
Yeah, N square.
Okay, so this is also same n square. We can consider this. Okay, and last, this print statement. This print statement is a single statement, and it is not dependent on the input side, like input. Okay, it will run always one time because this is outside of the loop or totally separate. Okay, one time. If you add all these steps, so first instruction is taking 1 time plus second instruction is taking n time. Okay, I am not including that plus 1, so some function will change. Okay, but that will not affect total overall time. Okay, so here second step is running n square time, correct, and third step is running n square time, and last step is running 1 time. Okay, so total steps are, we can 2n square plus n plus 2. Okay, this function we are getting. Okay, so this is the relation in the terms of input n. So this function is representing how many times our instructions, how many instructions we are executing for n input. Okay, so this is a function. Is it clear? What is the meaning of function here? Just a relation in the terms of input, and this is representing the total number of steps our algorithm is taking. So in these terms, so we got the function, and now, okay, now for the calculating the complexity actually. Okay, so for the relation, we generally takes the highest order of relation, so this magnitude n square, and we ignore the lowest dependency, so this n plus 2, and we also ignore this constant part, and we only are interested in this n square things. So that is representing the highest dependency on the input. So that means if our n value is changing like 1 to 2, so number of instruction will be changed from this way. Okay, so n square, so 1, and then next is 4. So this is called as a growth rate of function. Okay, so how our number of steps are increasing if we are increasing input size. So that relation actually we have figured out here.
Sir, can
Okay.
you please explain last 2 steps? Last 2 steps.
Last 2 steps means this function is clear, 2n square plus n plus 2.
Yes.
How
sir.
we got this?
Yes.
So for complexity, time complexity, so we are only consider the highest magnitude of n, this n square. Okay, so in this all terms, this is the constant part, this is also n, but this has the less magnitude. Okay, and this is the highest magnitude n square. So we only taken this to represent our relation.
Okay.
Okay,
And
how?
sir, why are we not taking n plus 1 as the terminating point for I in range n?
So many of the students have confusion about this, how this one is coming, so I have just ignored. Anyway, for theoretical concept, we ignore the constant terms. So if this n plus 1, this is we are taking, later on we will ignore that. So if we are considering that n plus 1 terminate condition, so we will get this function value. Okay. Still here we will only focus on this n square part. Okay. Here also we are getting the same n square.
Hello, sir.
Yes.
Can you please explain that n square part, sir?
N square part means you're not able to get how you are getting this n square.
Yes, sir. It should be n plus 1 the whole square, no, right, sir?
Sorry, what is n?
It's n plus 1 the whole square, right, sir? Why it is n square?
No, I have ignored the plus 1 from the every steps.
Okay, sir.
Okay, so I am considering on the loop range only n steps, not n plus 1 now. Because of that I have calculated this. Okay, so if you are not able to understand that what is the termination condition, because of that I mentioned this C example. Okay, so C you can clearly see one last termination condition will also check. That is the additional step where we stop our iteration. Okay, our loop will terminate actually. That is the additional step. Here, this in the Python is actually very easy language. So if you are just looking only I in range n, so range is provided some set of elements, and we read each element one by one from the set, and when our elements completed, so then we stop the process. Okay, but still some internal checking is happen when our elements are completed. Okay, so then additional steps comes, but that is not very visible here. So you can ignore this, but what I am trying to just explain here, just understand that how we are calculating the total number of steps. You can just ignore some constant operation here that will not affect overall relation. So this is the overall formula we got, and 2n square plus this 2n square plus n plus 2. This is called as a function. Okay, so and this here n is the input actually. Okay, what input size we are taking. So this is representing the exact number of steps. We can consider this as a function. But for the complexity, time complexity, we are only interested of the highest order magnitude of this growth. Okay, so n square part, this part, and we ignore the remaining part.
So what if there are two nested loops?
So okay, so then it become a NQ.
No, one set of nested loop. Again, outside that loop, there is another set of nested loop.
Okay, so
What is the complexity?
It won't.
So I am not coming at the complexity right now. I'll take some example also later. So you are talking about what type of loops. So suppose one loop is running like for I in range n. Okay, inside this you are running like for j in range n, and you are running one more loop.
No. Outside this for loop, outside this, I'm running another loop.
Okay. You
separate for
for
loops.
like this type of for I in range n. Correct? Outside of this.
And one more, and nested as well.
Okay, again
Another
nested. So
loop.
for
Yeah.
in
So there are
range.
two n squares in this case.
So this is actually sequential type. Okay, so here once this will finish, then this will start. Okay, so overall steps for this, actually what number of steps will be there? So this is n times, but this is n square time, correct?
Yes,
And
sir.
same, this is n time, this is n square time, correct?
Yes, sir.
And now just add all these. So 2n square plus 2n, you are getting this function.
Still n square. Yeah.
So
Okay.
the answer is n
Still-
square for this?
Still n square.
Okay. So no matter how many nested loops are there, the highest order will be the answer.
Highest, always select the highest order.
Okay. Got it, sir.
So that type of example I'll give in the next coming part. Okay. So I hope you got the idea what is this function represent and how we are representing the relation actually, proportional order of growth.
Yes, sir. Got it.
Okay. So let's move to the next part.
Why are we only taking your higher powers? I mean, because we want worst case. That's why we are only taking higher power.
So this is as I mentioned that this time complexity is not represent the exact calculation, exact time. or exact number of instruction. This represents the how our number of steps are growing when we are increasing our input. So that highest relation actually we are only looking for here in this concept. So because of that we ignore the lowest, that constant and coefficient, just looking on the highest order of terms to represent the Fn is proportional to n square, so to for this actually. Okay.
Sir, is this kind of things are important for quiz or not? Like this time complexity and these basic things.
Quiz. Yes,
Yeah.
it is important, and it is important for the whole course.
Okay. I'm not asking in general sense, like I'm not asking in the fundamental sense. I'm asking in direct question sense. Like for example, do we get questions to calculate time complexity in the quiz or
You can expect this type of question in exam.
okay, thank you.
Okay. Yeah. So I think some questions is given in your activity graded assignment. One
Sir.
activity assignment we have released only for this timed complexity calculation.
Sir?
Yeah.
So every time we need to calculate this type of equation so that we
No,
get
no,
a
no.
time
No,
complexity.
no. This is just giving the idea what is function represent. Otherwise, after some practice, you will only look on the highest order relation. So only you need to look only the loop part or something.
Okay. And one more question, sir. Only loops create a time complexity, na sir?
No, other things is also there. So we also have some recursive functions. Okay, so that in that case we calculate the complexity in different way. If
Okay.
our function is recursive, then we count basically our calls also, how many times our calls is happening, and
Okay.
with each call how many operation we are performing. So that calculation is different. But for the normal code, generally we looks on the loops actually, and how loops is incrementing. What is the relation for incrementation?
Okay, got it, sir.
Okay.
Sir,
So yes.
sir, like the higher the power of the n, that much more time it will take, sir.
Correct. So here this is a comparison. So and you can simply compare them which is the highest complexity. So you have n. Okay, this is the smaller, then n square, then n q. Okay, so if you compare all these three, so which is the highest complexity here? So if our input is n, like input is 10, this is representing number of operations. So any operation means 10 operation will perform. But if your complexity is this, so that means for input 10, 100 operations will be performed. 100 steps will be performed. You can consider this. If this is the complexity of your code, that means 1000 steps will be performed for input 10 size. So which one is growing faster? Okay, so this is the higher complexity compared to each. So that is we will some common complexity we will also see. What generally we find out most of the complexity. So I hope this comparison you understand that n square n q or 2 to the power n. This is the highest one.
Yes, understood, sir.
Okay. Yeah. So now
2 to
this
the
is the
power.
first part. 2 to the power.
2 to the power n is highest than n
Highest.
square n cube. Oh, wow.
Yes, correct. And also one more thing.
Oh.
Do not look this growing rate for the small input. Okay, we always looks this growth rate for the maximum or highest input. Okay, so maybe this n like n to the power 5 for 2 to the power n. So okay, so maybe for a small value you will get that this is the smaller, like if you're taking 2, and when you're calculating this, so you are getting 2 to the power 5 and this is 2 to the power 2.
Yeah.
So here this is smaller and you are not getting the relation. But if you will take this n value, bigger value, then you will feel that this is very much higher compared to this.
What happened if it is 2 to the power log n? Then it is the smallest, right?
Yes.
Still it
So
is higher.
we always compare these terms with respect of big value of input.
Okay.
Okay.
Thank you.
Yeah. So that next is notation. So we got this idea. We are only focusing on the highest order of magnitude for the complexity and from the function. Now the representation, how we represent this complexity. Okay. So what are the notation we used for this? So basically these three notations are there. Uh, big O and this big O terms, and we called this as a upper bound. Omega, this is lower bound, and theta tightly bound. Okay, what is the meaning of this actually? So here some definition is fixed for this when we will represent our complexity. So just remember this fn is representing a function. Okay, this fn is representing a function. F, we are representing fn, which we have calculated before. Okay, theta. But when we will use big O, when we can use big O, when we can use this omega, when we can use this theta with the complexity. So that represents some meaning, and some definition is mentioned for this. So let's understand this definition now by this diagram. Okay. So here for first graph. Okay. So not let's start with the second graph. Just understand big O terms. Okay. So here this graph is there. So here this side we have input. We are increasing our input. This size our time is representing. Okay, how much times of complexity we have. Okay, and this point is given n naught. This is some specific input. Okay, specific. Suppose we are starting from like 1 2 3 for some like n equal to 10, and then after that we are increasing for the bigger value, this input size. So if we have like this is the actual function, what our algorithm is taking fn. This is the actual function, and this time is the upper bound, like as a worst case. This is the maximum time when our algorithm will reach actually. Okay, in the worst case situation. Okay, so if you can figure out this term cgn. Okay, so this is similar to your fn. This is so what function we got for this fn things. If you figure out the cgn terms, so this is like a upper bound. Your algorithm will always take lesser or equal to this time in any type of case, worst case, best case, or average case. Your algorithm will not cross this upper boundary. So this time we have figured out that your algorithm will not cross this boundary for any input after this n naught point. If you can prove this, then you can write your complexity like this: fn equal to big O gn, and this gn is representing the maximum time by your algorithms, maximum time complexity. But we have to prove this actually. This is the maximum upper bound of your algorithms. But right now you can understand that your algorithm will never cross for any worst case situation, any input case. Your algorithm can reach till this bound, but it will not cross this. It will always smaller than this or equal to than this. So this is the actually condition for this. If your fn time, this is the actual time, is always less than equal to this cgn, this is the condition. Okay, then you can write your complexity like this with big O. Okay, gn, and this big O is represent a worst case complexity. Okay, I'll take one example to explain just one proof for this. So this is representing a worst case time. So maximum your algorithm can take this complexity. Yeah, Himanshu.
So, sir, what this means that our algorithm can take minimum time proportional to this theta of gn, maximum time to the big O of gn.
No, theta is a representation, but gn is the terms actually. If we are representing this big O, and this gn is also represent the highest order of magnitude, not the complete function. Okay, we will always represent the complexity in the one term, not the complete expression. high, or that term will be the highest magnitude term.
Okay.
Okay, but we have to prove this condition. What condition I have written here? This fn should be less than equal to cgn. If we, and here c is a constant, okay, some positive constant. If we can prove this, then we can write our complexity with big O, and that is representing a worst time actually for this. This is the maximum time our algorithm can take.
Sir, is theta like the combined version of big O and the
So I'm coming
omega?
on that. I'm coming on that.
Oh,
Okay, now I'm moving to the second, this last diagram. See, so here the condition is different. Okay.
Sir, a doubt, sir. Like for the big Go case, sir.
Hmm.
In case if we are just doing it up to n equal to 10, then like for small values, it will not work, sir.
N equal to 10. No. We actually, I have said that don't consider this for any specific.
No,
Okay.
sir. Like for n equal to n naught, when it is like small, then both will be like same. Like in the graph, for example, they are the same
So
point,
this
sir.
this fn can reach till this. Okay, so this can touch this upper bound. So because of that, we are saying this is a upper bound. So this is the boundary actually. Our algorithm can touch this but cannot cross this.
Yes, sir.
Okay,
Understood,
it
sir.
will always less than or equal to this. So this condition is given: fn may be equal to this value or always less than, but not greater than.
Yes, sir.
So okay, now then we can represent our complexity with big O, and it will represent a upper bound or upper maximum time complexity. Okay, now theta, just omega terms.
Sir.
Okay, so omega terms is different.
Sir, what is C?
C is a constant, any positive constant, 1 2 3 4 5 kuch hai, anything.
So we can't take directly Zn.
So that I'll take one example to explain this. Okay, so what is this we can prove? First thing, just understand that omega terms. Okay, omega notation when we can use. If we can prove our fn, actual time of algorithm, is always greater than or equal to cgn. Okay, that means this time we are figuring out the minimum time by the algorithm. Any case when our algorithm will take the minimum time after this input, okay, n naught point. So this should be satisfied after this point for all range. Okay, so any value for n, this condition should be satisfied. So fn will always be come either greater than this or equal to this bound. So this is called as a lower bound or lower time, minimum time for this algorithm. If we can prove this, then we can represent our complexity with omega. Okay, this is just like a best case. Okay, now theta is the case if we can prove both condition. So that means fn will always be less than equal to c2gn, and it is always greater than or equal to c1gn. That means this fn time will always be lies in between these bound. If we can prove this okay, and this bound, so we can represent our complexity with theta. Okay, so this is the time like this can reach till this point lower. Okay, maximum this and minimum this. Here we are only just calculating based on the upper time. Okay, and this is the lower side minimum. So generally in the short we call this as a best case, this as a worst case, and this is the like as a fixed time or tightly bound. Okay, now I'll take one example. Okay, we can take the example for previous function. I'm removing these condition. So that function we got this. Okay, so let's prove this, how we can represent the complexity for this. So like 2n square plus 2n plus 3. So we have this function fn 2n square plus 2n plus 3. Okay, this function we have, this is the actual function for our algorithm. Now our target is to figure out, so suppose we want to represent the complexity with big O notation. So we have to prove our condition like this: Fn is less than equal to Cgn. Okay, so Cgn. This condition we have to prove. So that means we have to figure out one term, Gn, and with some constant. So C may be any positive constant with greater than 0. And here one more position is there, n naught, okay, which you have seen in the diagram. So this is the point. We will always look the value which is greater than this, okay. Then this condition should be satisfied. So this n naught value is also need to calculate. So after this n naught point, this condition should always be true. So then we can conclude our complexity Fn equal to big O Gn. We can write like this. Okay, so let's start with, okay. So now we have 2n square plus 2n plus 3. This is the mean time function, okay. So this is a Fn. Can I write this like equal to, if okay, if I replace this n, okay, so I'm just writing like this: 2n square plus 2n plus n, okay, and I'm taking one input n equal to 3. I'm taking n equal to 3. Now can you see this right part will always be greater than or equal to this for this situation? Not n equal to 3, n is greater than equal to 3, like this, okay. If I put this 3 value here at the place of n, so both will become equal. If I am taking any greater value for n, like 4, so this part will be greater.
Yes.
Correct?
Yeah, yeah.
So I am figuring out the Gn terms, okay, but we will do the process to prove this, okay. So I have taken this situation, just remember this, I have taken this first condition. So now 2n square plus 2n plus 3, this is the Fn, but we can write like 2n square plus 3n, okay. I have added this. So this is true for this value, okay, n is greater than equal to 3. Now I just reduce this term also in the terms of n square, because we are only focusing on this highest order of magnitude. So let's just replace this 3n with n square, okay. Can I write this like this: 2n square plus n square, okay. Now I am taking the condition if our n square is greater than equal to 3n. Okay, so this relation we are maintaining here to check this. If I take n square equal to 3n, both will become equal. But if I take greater than this, so this part will be greater. Okay, if I take 3n plus 1, then this become a right side become a greater part.
Yes, sir.
Okay, just compare these two conditions. We have already performed comparison from this part, but now we are looking this part. So I am replacing our 3n to n square, and I am taking this condition: n square is greater than equal to 3n.
Sir, why
If
we
I
replace, sir?
so we are figuring out Cgn term. Okay, so this should be of the highest magnitude of n term. Okay, so we are reducing our expression in the highest order of n term. Okay, but that should be satisfied all these conditions. So this C should be greater than 0, and we will also figure out this n naught point. Okay, to prove this, we are just figuring out the upper bound function. Okay, so I'm writing this like 2n square plus 2n plus 3. This was less than equal to 2n square plus 3n for n is greater than equal to 3, and this is less than equal to 3n square. Okay, I have just added this 3n square, and this is condition is n square is greater than equal to 3n. Okay, now this relation we got, and this value we got. Okay, 3n square. Now you can just relate this as a C, okay, this term as a Gn, Okay, now you need to identify this n naught point. So we have considered 2 points actually. So n is greater than equal to 3, n square is greater than equal to 3n. Any value of n which satisfied both condition. Can you figure out?
Actually, both says n greater than or equal to 3, right, sir?
Any specific value, any we can take one here, so which will satisfy both? No, no.
No.
If we take
Actually,
no, if
both
we take
conditions
n
say
equal to 2,
n, sir. Both
huh?
conditions says in both conditions says n should be greater than or equal to 3. In the second condition
Huh.
as well, right, sir?
Huh. So this condition we are taking to prove this actually, but we have to figure out some specific value for this, no? What value we actually n naught we are figuring out? What is the n naught value? So when our after this n naught value, our this condition will always be true actually. So for this two condition, if I take n equal to 3, can you see both conditions are now become true?
Yeah.
Yes.
Okay, this is also true. This is also true. So this become a n equal to 3. After this n equal to 3, if you take any value like 4, 5, 6, both will be 2. Correct?
Yes, sir.
Okay. So now this is the n naught point we can consider. So n naught is a equal to 3. So here to prove this, so this was the fn. Okay, fn, and this is like a cgn. This is less than equal to cgn. Okay, cgn means 3 and n square. Okay, so this is now c, this is gn, and n naught we have figured out 3. Now this conditions are proved. So what is the gn value? This is n square. Okay, if you have proved this, you got all this constant n naught point. So that means for any value after this, including this 3 and after this 3, this formula will always be satisfied. This fn is less than equal to cgn. So this 3n square, so this fn part will always be less than or equal to for every value after this 3. Okay, so we have figured out this upper bound, and then this formula is satisfied. We can write our complexity with big O notation like gn. Gn is n square, like this.
Sir,
Okay.
one doubt, sir.
Yes. Yes.
Yes, sir, in case like if just a minute, sir.
So you can prove this in different way. I have taken this step like this. If you can prove in by some taking some different steps, but that should be satisfied actually. But overall, I got this point. Okay, and I'm saying this after every value of n3 and 4. This condition will always be true. So that means this part, this side, we have the upper bound. Okay, and this was our goal to prove. We are just looking the upper bound to represent our complexity with big O.
Sir, in case like if you're having some other function like which has the maximum power as n cube, sir. So
What
then,
example?
Sir, something randomly, sir. I'm asking like if in case we have the highest power, like whatever n cube or n power 4, in that particular case, gn will always be the highest power value of it.
So we can consider this part. So this gn is always be greater than to this fn highest order, or maybe equal, but not less than. So our like this fn may, so this condition cannot be happen. So like this fn is like a n square. The highest order of this fn is n square, and we are getting gn like n. Okay. When we are just writing the complexity with big O. Big O means this side, this gn should be equal or greater than to this n square, this fn part. Then we are only able to use this big O notation.
Sir,
Okay.
like for
So
example, the function has.
I'm just giving the example. Suppose if fn is given like n square, if gn is given like n, So can you, so this type of question is also asked in the quiz. Okay, so if these two functions are given, fn and gn, fn is given n square and gn is given n. So what represent is this 2? So can we write gn equal to big O fn and fn equal to big O gn? Which statement is true? Which statement is true when we have given this two value, fn equal to n square, gn equal to n? Which statement is true?
Sir, first statement is true, sir.
Yes.
First statement is true because we are using big O notation. So that means this part should be greater than or equal to the gn, but it cannot be less than. Okay, so fn part here is n square and this is n. So this is okay.
Like for
But
second
this
case,
cannot be.
for second case, if we use omega, it will be correct, no, sir?
Then it will be correct. Yeah. So according to the definition, that should be satisfied here. So this big O is not representative because this side gn is n, but fn is n square. So that is not maintaining the definition of big O notation. Okay.
Sir,
This is
like
not
till
possible.
this, it's clear, sir. Like I have
Hmm?
another doubt. Till this, it's clear, sir. I have another doubt. Like, for example, f1 is like n cube, sir. Like maximum thing is some function, but it has the maximum power as n cube. And
Plus something.
yes, sir. And in case we are getting gn as, can we get gn as n power 4, 5, something like that, sir?
Okay. Yeah. One more thing. Okay. Yeah, that is also correct thing. To prove this, so what is the condition actually for the big O notation? So condition is fn should be less than equal to big O gn. Correct? Sorry, less than equal to gn, cgn. Okay. So here upper bound means this should be always greater than. So this condition, if this condition is satisfied, so for this case we satisfied for this n square, this part, and this is also we got gn is also got v n square. Is this condition will also be satisfied for if we found that gn equal to n cube. Still this formula will be true because this will always be satisfied, because this upper bound means our algorithm will reach at the equal this upper bound, or it will always be lesser than. So this lesser condition is also there. Correct? So if we are taking gn equal to n cube, still we can write our complexity for the same function big O n cube. That is also correct. But for complexity representation, we always looks the closure upper bound, not the any upper bound. So we so for function fn equal to like 2n square plus 2n plus 3. We have just proved the complexity for this is fn equal to big O n square. Correct? Okay. So this is representing upper bound. But this is also true. Big O n 4, like. Because according to the definition of big O, this side is greater than to the fn side. Okay, this is the condition for big O. So this is also true. We cannot say that this is not correct. We can also write for this fn equal to big O n to the power 10. This is also a upper bound because our fn will always be less than this. According to the this definition is satisfied. But for complexity representation, we always looks the closure upper bound. So closure means, so closure upper bound we can prove only this n square.
Got it, sir. Like whenever we are finding this, we get the closest little upper
Closure upper bound. When we will represent our first time complexity, that should be the closure upper bound, not the any upper bound. According to the definition of big O, these are also true. This is also true. All are actually correct. So upper bound means our complexity cannot cross this. Our algorithm function time cannot be crossed that bound actually. So our algorithm is not crossing this also, not crossing this also. So that means we can represent this big O n to the power 4 also. But we are only interested to representation for the closure upper bound.
Sir?
Yes.
So at Fn is equal to Gn, all three are correct. All three representations are correct.
But we have to, if you are just writing anything, you should have the proof.
So
Okay,
what
so
proves
like means this condition should be satisfied for by your proof. Okay.
See, sir, if n square is equal to n square
Huh.
comes, so in
So
that
you
case,
should be able to prove this condition CGN. You should be able to, for any constant, positive constant this and any n naught value, you should be able to prove this either equal or either less than. So this part should be always less than or equal to the CGN. So your you should have some proof for to satisfy this condition. Then you can write your complexity Fn equal to big O Gn.
Sir, can we write this as same as omega of f of n equal to g of n?
So that now the condition for the omega is Fn is greater than equal to Cgn. Okay, this is the condition. Now C should be the positive constant and you should have n naught or some point. Okay, any point. So now
So can we write that omega of f of n is equal to
so
g?
n equal to like this is very easy proof actually. 2n square plus 2n plus 3. So if you can write this, suppose we are figuring out the CGN part, okay? So we can directly, so because this part is the additional part, okay? So we can directly write like this condition. So this is always greater than equal to 2n square. You will directly take in this. Okay, so this is Fn and greater than equal to, we can consider this as a CGN. C equal to 2, Gn equal to n square. For any value, n is greater than equal to 1. So this become a n naught. This is true. Okay, because any value, if you are taking n equal to 1, so this additional part, this will become as a bigger value and this will be the smaller value.
So can
Okay,
I
n
write
equal
it
to
as
n
omega?
Then so this is the proof for omega. So you can write complexity Fn equal to omega Gn. So Gn is n square, like this. And for the theta condition is if you have both proof. Now you, for the same function, if you can prove the upper bound condition, if you can prove the lower bound condition. So now for this case we have proved both. Then you can also write your complexity with theta Gn. So that means so here you can just look like this. So Fn is should be less than equal to C 2Gn. Okay, so we are taking some different constant here. So Gn, and this should be less than equal to C1Gn. So we have also proved this. We have also proved this. So we can write also our complexity equal to theta Gn. So Gn is the same for both condition. So that is n square. That you can also write this notation. So this is just a use of notation. And what your complexity is representing by the notation. If you are using complexity big O, so with the notation n square, so that is representing a worst time actually by your algorithms. Okay, for any input. So mostly actually this big O is used. Okay, but you should also know about the theta and omega. But most of the time you will find that this big O is used because our main focus is only for the worst case time complexity for algorithm, and that we want to reduce actually for the efficiency. Okay, so during the course we will only see our complexity with this notation.
So before starting this derivation, you have taken 3 is equals to n. Can we take 3 is equals to under root n or something else?
You to prove you can take anything. So here what actually I have done, I have just replaced this 3 term. Okay, n is greater than equal to 3. What you can do, you can directly take this condition. So you can take n square is greater than equal to 2n plus 3 and just replace this part. Later just prove for any value which satisfied this condition. Okay, so to prove this you can take any steps, but you have to come to this condition. Okay, so you have to just satisfy this condition. What is the expression for the big O actually? So this is the idea of notation. We will not always calculate like this. Okay, so for complexity, we will not always calculate the complexity like this complete function, then we are proving everything. But you should have the idea if this type of question comes, how you can move, how you can conclude this. Generally, when you are giving any subjective exam, like okay, so this type of questions ask some function is given and they ask like just prove this function fn equal to big O like n square. Some function is given fn something and they generally ask just prove this. So you have to write the steps to satisfy the big O notations conditions. Okay, and just set just prove this omega n square. So this type of questions generally asked in the subjective exam when they ask for the proof thing. But for normal complexity calculation, during the whole course, generally we use this omega big O notations, and we will only focus on the highest order of n, which our algorithm is taking by the loop and all this recursive function, all these things. Okay, we will not go in that much deep for the every time complexity calculation, but you should have the knowledge for this. Subjective exam, no, we don't have the subjective exam for PDSA. We have the MCQ type of exam. But I am just giving you as a maybe later you will just learn any additional course, maybe a master degree or something. And when we will do this type of course, that there is a chance you will get this type of proof type of questions. Okay, so now this is the idea of the notations. Basically, we will use in our course this big O most of the time. But now maybe you got the idea of when we use the omega, when we use the theta. Okay, can we move?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, now you can see we are focusing on the big O notations only. So these are the some common complexity in the terms of growth rate. Okay, so which one is the fastest growing actually? So this is the smallest time. Most of the time you will see your complexity like similar to this terms. So these are very common terms. Okay, so this is called as a constant time. Okay, constant means your number of operations are fixed actually, and it is not changing for if you're changing the input. So like so this big O 1, this is looking like a 1 steps, but this is not the meaning of this. Big O 1 means constant number of time. If your algorithm is performing 5 steps, okay, suppose 5 instructions, but that is fixed actually. If you are taking n equal to 1000, still it is performing 5 steps. If you're giving like n equal to 10, still it is executing 5 steps. So we will not write our complexity big O 5. Okay, so we will just maintain a complexity big O 1. So that represent a constant time, fixed time. That is not changing by the input. So this is the meaning of this. Big O 1 means constant time. Okay, log n, log arithmetic time. So how we I hope you have checked the binary search algorithm. So how much steps actually we can get the solution. So suppose n equal to initially are suppose 1024. Okay, we have these number of elements, but according to the logic of binary search, every time we check the middle element and we remove half of the searching part. Okay, half of the input size we removed actually. So if our searching element is either greater than to the middle element or maybe lesser than to the middle element or maybe equal to the middle element, based on these 3 conditions, we remove the half of the input size for the next checking. So next time this size becomes a 512. Okay, next same things. So I'm talking about the worst case situation. Okay, so there is a chance you will get your searching element in 1 step. So that is the best case for the binary search. So but worst case situation, this will reach to the 1 actually 512, then 256. Okay, and then 128, then 64, then 32, and then 16, and then 8, then 4, then 2, then 1. Okay, so how many steps you are getting? You have initially n equal to 1024. elements you are searching. But in these number of steps, you reached at the one element for looking. So how many steps actually these are? You can relate this to the 1024. So this is like a logarithmic time. So that means log base 2 1024. So that you can represent 10 to the power 2 to the power 10. Okay, so that is now 10 become here, so 10 steps. Okay, so log 2 and 2 will become a 1. So 10 steps you are reaching, you are terminating your process, and then you can represent this complexity as log n steps. Okay, so I hope this is clear. When generally we got this type of log n complexity, when your steps, your size is reducing half at every time. Okay, or maybe you are suppose if you are starting with 1, every time you are doubling your value. Okay, suppose n is given like 64, and every time you are doubling your value 2, 4, and next step you are moving to 4, then 8, then 16. So you will reach at the log n steps to this 64. Okay, this type of case, when you are every time removing half of the input size, okay, reducing half size, then it become a log n. Or if you are doubling your steps, okay, to reach at the last point, so then it become a log n steps. And linear time, so like we are just searching element in the random list, okay, unordered list. So step by step we are checking each. Okay, so that is just like a linear one loop. And log n time, yeah, this generally comes with the divide and conquer, like merge sort algorithm. We will discuss this. So we have some n operation, but we are recursively solving the each half part. So that I'll discuss this. N square, we have already checked this nested loop, 3 time cubic root. Okay, so this type of complexity, this is exponential time generally called. So this we will also see. This is also comes by the recursive calls. Okay, so that I'll also give the example for this. And this is the maximum factorial time. So this is increasing like this. Okay, so this one is the maximum, this is the next maximum, like, and this is the smallest one.
Sir, I have a doubt. If we divide by number 10 or 9 or 8, something with the same number, is it logarithmic, sir?
Sorry, 10, 9, 8, what you said?
For example, first we are taking 1000 and divide by 10, it is 100. Now it is dividing by 10, it is 10. Like that.
So
like
that we also consider as a log n time, because okay, suppose if you are dividing like 100 by 3 at every steps. Okay, so you will reach at the 1. So that is generally similar to this log base 3 n. Okay, not base 2. So, but as I said that we can represent the upper bound in the terms of this upper bound is represent the maximum limit. So generally we represent this type of complexity also with the log base 2. That is the higher than this, okay, log 3. So we can represent this. Otherwise you can also write this complexity with base 3. So that is also correct.
Okay, sir. Thank you.
Okay. So I think some mathematical proof is there. So if you have log 3n with some additional constant operation, you can compare to this log 2n. So you can make this to a log 2n. Like this, some mathematical proof we have for this. You can search that. Okay, so now comes to the calculating complexity. How generally we calculate the complexity? Okay, we will not calculate all the things every time because this is totally theoretical concept. We will overlook on the code and we will just figure out the complexity, how our loops are running and how our loops are depending on the input size, and based on that we will directly return our answer. Not we will calculate each steps or each type of things. One thing, this example, just look this. Okay, what is the complexity of this? If we are changing, so for suppose this A, this is a simple sum example. Okay, so here we can consider our input like A and B input. Okay, so input A may be changed like 10 to 100, B equal to maybe change like 20 to 2000. Our total number of steps will change if we will change our value of A and B.
No, sir.
Okay, so this type of codes, when our steps count is not changing based on our input value, so that is actually a fixed time, and we can represent a constant complexity like big O1. Okay, so move to the next. Suppose this second code is given now. Here, just conclude that and always look the highest relation. Okay, you can ignore the constant things. Just look the highest order, which is represent the relation. So for second, complexity is given, but just you can figure out that. So here we have one constant operation. This is taking one time, and this part actually, okay, this part is n, or inside this is also n. Okay, so this is 2n. So remove the constant part, n. Okay, n is the complexity for this overall. For next code, so this is taking n, but internal part actually this is n square, this is n square. So what is the highest order? N square. Overall for this become a n square. Any doubt in these basic examples? We are just looking the highest count actually, which is depends on the our input. Okay, so let's move to the next. Okay, how much for this third one?
Thank you.
Thank you.
Why n cube? Because this part actually, this internal part will run n cube time. Okay, so because of that we are taking the highest. Now the example of different parts. Suppose if you have multiple blocks of the code in your code. Okay, so let's this part. Okay, I think someone have asked this type of situation. So you can see here we have multiple loops, but these loops are running sequentially. Once the one part will be finished, then second part will be start. Okay, so this loop, this is totally separate part, and this is again totally separate part. So you can just calculate the each part of your complexity. If these parts are not like dependent on the other, it is running sequentially. Well, one is finished, then second will start. So what is the complexity we have already seen for this type of part? N. Okay. For this part we have
N
seen
square.
N square.
For this part we have seen n cube.
N cube.
Cube.
So overall complexity will become a maximum of n cube. For this complete code, overall complexity will become n cube. Okay. So in this way, most of the normal code. So okay, so I'm just writing a one small code here. So for okay, run a while loop. Okay, so if I equal to like 1 here
Sir.
while sometimes,
We are not denoting this in a big O notation. That means the complexity does not exceed the n cube, right, sir?
n cube. So this is the upper bound. We can see that we can represent our complexity with upper n cube. Okay. So this is the highest order of n gn. Actually, you can consider this here.
So if we use omega, it means n, right, sir?
Omega. Okay, lowest. Okay, so how you can reach right like as a n?
Because it is the lowest.
First, you have to write here the maximum upper bound. Na? So same omega also will come and q for this. You can write like this. Omega, you can write n. This is also true. But as I said that we always look the closure bound. Closure upper or closure lower bound. Not any highest one. Okay. So here big O nq is true. The big O n5 we can also write. That is also true conceptually. But closure one is this nq. So we will only write this as a complexity. So same thing here. Omega, if you are representing the complexity, because of that I mentioned that now only focus on the big O part. Don't move into too much with the omega or anything. this is just a notations. Okay, and don't confuse too much. I have already mentioned that what is the meaning of this. You should understand the meaning, but don't calculate the complexity in every time for each, like theta, omega, all these things.
Okay, sir.
Okay, so here I am just writing a loop, one example. So while okay, we have the starting point I equal to 1, and running a loop, so like I is less than equal to like 100 something. Okay. And inside our loop, we are incrementing our value like I into 2. So this is also a iteration, but here this time our number of iterations are depends on some condition. So this is just like a normal linear loop incrementing by 1 every time. But what happen if we are incrementing our loop variable by doubling or this type of situation? So this is not a linear actually. Okay, so suppose if I'm taking n here. So here we cannot write complexity before directly n. This is not a closure upper bound for this, because this loop is not running a linearly like one increment. This loop is doubling it every time. Okay, so I1, now next time it will become 2, then 4, then 8, then 16, in this way, and it will reach to n this terminate condition early. So total n steps are not required, so less steps are required, and it will reach to this terminate condition. So how many that steps are required, so that we can figure out based on this incrementing condition. Okay, so that is log n steps. Okay, so in this way this complexity can also be represented.
Sir, can you repeat the log n part?
So when you are starting for this loop, you are starting for 1, but increment is happening doubling. Actually, you are doubling your previous value every time. Okay, and this is the terminate condition. N is given with the terminate condition. When I is less than n, you will enter into the while loop. So here total n steps will not perform. Steps will be performed like I equal to 1, then 1 become a 2, then 4, then like 8. So in this way your value is increasing in the I, and you will reach at the, suppose n equal to 64, so like 16 and 32 and like 64, you reach the terminate condition only in this 7 or 8 steps. So n was 64, but your loop number of iterations are only 7 to reach this terminate condition. So here incrementing is different. If our increment is happening like this, I equal to I plus 1, so you will run total number of n iteration by this loop. But if your incrementing is happening like I equal to I into 2, so that is the doubling case. So that is indicating the log n steps.
So that means what operations we are performing that justifies the complexity.
So just identified that your first just check the loops part. Okay, for the normal codes, just check the loop part. Also check your loop variable, how your loop variable is incrementing. It is just like a one increment, or it is just like this type of doubling or something. So based on that, you can figure out the complexity, not just by looking. So this is a loop, so just directly return the answer order of n. Check inside here how your loop variable is changing. Okay, then you can conclude some that order of that n actually steps.
Sir, if that in that for loop in the left side, if we, instead of the s equal to s plus 1, we using that I equal to I plus 2, then it is not n square, right, sir?
I equal to I plus 2 is different. So
no, sir. I want to playing by 2.
So I think for Python, this is just like we cannot change the value of I. That is something wrong actually. If you want to change the steps, you have to write is inside this range formula. Okay, so just care about this. Generally, in the Python code, we not change the for loop variable within the code.
Okay, sir.
Okay, if you want to change the variable within the code, you will use this while loop. C we can do, but here in the for loop, it may give some wrong behavior. Okay, because this loop variable handled by this range actually. If you want to perform some steps, like you have to mention the steps in this. So this type of while based code in the Python where will can be changed inside the body. So that is you can consider. Okay, so this is the example for these. Now comes to the recursive part actually. So recursive calculation is different. So normal code, when code you have some simple iteration or simple calculation, you can figure out this based on the loops actually. Loops are the main important part here. But for the recursive code, we have some different type of calculation. And this recursive code time complexity, we will also understand in the week 8, actually how we calculate. But think here, this is the recursive solution. Okay, this part. So now this is the factorial code. You all know about this factorial, how we can write a recursive code for the factorial calculation. Now we have recursive call here. So this we also focus during the calculation of our total number of steps. So generally, one terms actually used for the recursive code, this is called as a recurrence relation. That is represent the relation of the time complexity or in the with the recursive calls. Actually, we also because we are calling first time, like we consider as a total time is tn. Okay, but to calculate the time, because internally we calling the same function again, so that means we have to calculate the time for that function also. Okay, so we have to represent our time complexity in the terms of this recurrence relation, which represent how every time, how many times we are calling the same function, what size we are passing to our recursive calling function, and apart from this recursive part, the remaining code, what is the time complexity for that code. So this recurrence relation is represent this information. So that means total time is equal to tn. The first part is the recursive call part. Okay, recursive call part. What is the time for recursive part? And second part is the, other than the recursive call, what is the time complexity of the remaining code? So that is the time for the remaining part. So this is the two part actually in the recurrence relation. So tn, where the n is the initial input. Okay, now just see this code. Okay, just see this code. How many times we are calling the same function? Times means how many calls are there inside this function? 1 or 2? How many calls are there?
N calls. 2.
No, how many times we are calling the same function from inside this?
n-1.
One time. No, not this. I'm not asking the input. Only number of calls. One.
So how can I get a number of calls if we don't know the n value?
So n plus 1.
No, I am not asking the total number of call. I am just asking from this part, how many calls are there? Only simple one code. This just look only this. One call only.
Yes,
This
sir.
is the one call, no? This is the only one call, no?
One call, sir.
Huh. So you will also see where we will call 2 times from our body, the same function. So I am just looking how many times call is happening from inside. So that is, I'll check this, what input size we are passing to that. That's the different things. But only one call is happening from this side. So that is just like a t another. So that means total time for the main call is tn. Okay, this is representing n. But we have also calculated the time for this part, this call. So again, we are writing t another call. Okay, so this is the time we have to calculate. Okay, but apart from this call, what is the complexity of the remaining part? This
1.
One constant time plus. So either you can represent big O 1, or sometimes you will also find only one, right, like this. Okay, and or 1 like this steps. So both are correct convention. Okay, so 1 steps it is taking, or this is also sometimes represent like this. So this is generally called as a fn. Okay, and this is the still we need to calculate. This is not the complete calculation part, but this is representing recursive number of calls, actually number of calls. So that means t one time we are calling the same function again, but what input we are passing? n-1 in the call. So this become a recurrence relation for this recursive function. So tn, this is the total time, is time for recursive call, this part, and additionally, apart from this call, we have the constant time. Okay. Now, this type of recurrence relation generally writes, we first write for the any recursive call. Okay. After then, we expand this recurrence relation to calculate the complexity. Actually, we solve this recurrence relation. How we solve this? Now you know that Tn is written. Okay, so I'm writing here. 1 second. Okay, delete. Okay, so I have calculated the complexity Tn equal to Tn minus 1 plus 1. Okay, so this is still need to calculate to get the final complexity. So as Tn was this complete expression, now this is a new problem. Okay, new problem with n-1 input. Now I'm writing this. If suppose if for Tn-1 is this, then what will be the recurrence relation for this expression? Now our n is changed to n-1. So just write the same things, only replace n with n-1 at each place. Okay, so this will become a t. Just write this n, convert change this n to n-1. So this will become a n-1 minus 1. Correct? n-2. And constant part will remain constant. So 1. Correct? So when
So
input was n, sorry.
why we are replacing n by n minus 1?
Because we are expanding this expression actually. So we are looking the time for this part. Okay, we are looking the time for this part. So this is similar to this Tn, but only the input is changed. Input size is changed. So we are writing the same expression for this Tn-1. So just at the end we have written n-1. So this is the main complete expression. So we will write this expression with this input n-1. So just replace n by n-1 at each place. So we are getting this part. So this means we are just replacing, because this is still a problem. We have problem with factorial like 5, and inside this f4 is called. Okay, so this is a new problem with different input. So we have to also calculate the time for this problem. Inside this, another new call f3. So that means this is another new problem with another size. So we have to calculate the time for this part also. Then we can only calculate the final overall time. So just time for n size input is representing this recursive recurrence relation. Now we will replace this Tn by this expression. Okay, so Tn now become so just replace this part with complete this part. Okay, so Tn-2 plus 1 plus 1. Okay, so this part I have replaced from this. Okay, now this is again a new problem. So just write like a Tn-2. So just change this n value, this expression, n2 replaced by n/2, n-2. That will become a T n, just replace n-2 minus 1. So this will become a n-3. And plus 1 will remain constant, because this one part is not dependent on the input. It will always 1. So now just replace here by this part. Okay, so Tn become a Tn-3 plus 1 plus 1 plus 1. Okay, so in this way we will expand this. Next time just replace this with next. Okay, so this is Tn-4, and you will get one more one. Okay, so plus 1 plus 1 plus 1 plus 1. So you can see, if we are starting n any value, suppose n equal to 10, every time one steps we are reducing. Okay, so one step, and this step, one step is adding here. So how many steps will require to reach at the t base case? Basically, every recursive call also has the base case. So either that is t1 equal to directly 1 or t0 equal to directly return answer something. So that is the base case for the recursive call. You can see. Okay, so here you can see this: if n equal to 0, return 1. This is the stopping step, one step. So that we are considering when our n becomes 0, it will directly return answer, and that is the one constant step. So we are just reducing these steps every time, and in this way, so n minus 4, so that means this value is coming here. Okay, so 4, if you add this 4, so that means to reach at the base case, so total n minus n steps are required. So n minus n steps are required, and at that time this part will become a n. Okay, 1 plus 1 plus 1 n times, so n. So this t n minus n will become 0, and this side you will reach at the n, or this is the base case. So base case is taking only constant time, so n plus 1. So overall time will become n. So we are expanding this type of recursive relation, but first step is you should know how to write a recurrence relation. Then recurrence relation you can solve in different methods. So there are multiple methods to solve this recurrence. This is the one method. You can just put the value again and again and just see what type of relation we are getting, if what type of series we are getting, and based on that you can conclude your total steps. But this time we are only calling one recursive call. So this is easy actually to solve. But we will also see the recursive call when we will call 2 times, like this merge sort. Okay, so merge sort, I'm not sure you have checked the merge sort algorithm or not yet, but merge sort have the actually 2 steps. One is the merge. Okay, this is the one steps merge, and what is the task for this merge step is just combining 2 sorted list. I hope you have done this at the time in Python course also maybe, but you have 2 sorted list. Okay, suppose you have like one list like 1 3 4 5. Okay, one sorted list. Second sorted list you also have 2 5 8 10 20 like this. Okay, 2 sorted lists L1 or L2 you have. Your task is combine to these sorted list into a one final sorted list. Okay, so output should be one final sorted list 1 2 3 4 5 6 8 10 20. This should be the output. So how you can do this task in order of n time? So our algorithms are not too much actually difficult. If you just think about that, you can just break your algorithm into some small part, then you can easily understand. So this merge sort, complete merge sort is just like a 2 part. One is the merge, and this is the problem actually. If you can solve this problem in order of n time, then your task is done. Doesn't matter what algorithm, what code you have seen in the lecture. Okay, that is professor style. If you can solve this problem into your style in order of n time, then that is also correct. Okay, algorithm is not just like a implementation. This is a task actually, how you can do this in order of n time. Just do this in order of n time, your work is also correct. Okay, so this part in merge sort is order of n time we can solve. Okay, and this is the another part of merge sort. This is the dividation part actually. This breaks the problem into different parts. So initially we have so this is sorting algorithm, mainly this is a sorting algorithm. And so initially suppose we have like 8 element. Okay, we have 8 element like 4 3 8 7 1 2 9 5. Okay, suppose this element we have. So we are giving this element list to the merge sort. The task of the merge sort is just break this list into two different part, or this process will happen repeatedly till when our list will become a single element. So first part will become like 4, 3, 8, 7. Second part is 1, 2, 9, 5. Now this will again break. Okay, this is recursive call. Okay, so this is recursive call. So this will again break 4, 3, and this is 8, 7. 1, 1, 2, and 9, 3. Again, this will break. Okay, so now 4 and 3. 8, 7. Similar to this, 1 and 2. 9 and 3. Why we break this till this point? Because our merge operation is performing merging two sorted list, and when we are reaching to the last single element, we can consider this as a sorted list, because single element is sorted, no comparing element with this, so we can consider this is a sorted list. Because of that, we are just breaking this list to the last single element. Okay, now from this point, whenever each element becomes a single element, now we can consider that this is a sorted list, two sorted list. And now our merge process will call on this. So now merge process is taking two sorted list and combining into a one sorted list. So that is a merge operation is doing in order of n time. So two steps are there. So in 2 steps, it will become a 3 and 4. Similar call will happen with this part. Okay, so this will become a, both are 2 input sorted list. Now it becomes a 7, 8 by the merge process. Okay, same will happen with this, 1 and 2, and same will happen with this merge call, 3 and 9. Okay, now again, yes.
What is happening here? Just ascending order?
Sorted means ascending order.
I mean, you just wrote everything into single lists and you just put it in ascending order in groups of 2.
So that is the task of merge function actually. So merge function is taking 2 input that both 2 lists, both are sorted, and it is combining into a one final sorted list. So from this point, when we reached at this level, now this single element is will be considered as a sorted list. Here from merge function will call, this function will call. Okay, now this function will combine this into a one final sorted list. Okay, clear?
Yes sir, yes sir.
So merge function is called at this level because this is the condition. You can see this is the terminate condition for this recursive call. Whenever n is reached at the 1, we are directly returning a. Okay, we are not calling recursively again. So that means when we reached at the single element, we are directly returning, and this returning is happening by the merge function L and R. So this 2 function will be merged by this call, and this will combine 2 input sorted list to a one sorted list. So this will become a 3 and 4, and this will become a merge sorted list 7, 8. Okay, this is 1, 2, and this is 3, 9. Now again, this is because this is a recursive call. This will run like this. So now again 2 sorted list you are receiving. Okay, 3 and 4, 7 and 8. Merge function will again merge this to a one sorted list. So this merging will happen 3, 4, 7, 8. Here same merging will happen with these 2 input sorted lists. Okay, so this is 1, 2, 3 and 9. Okay, now you got the 2 sorted list. So again this will merge into a one final sorted list. Okay, so that will be actually 1, 2, 3, 4, 7, 8, 9. 1, 2, 3, 4. Okay, 2, 3 are there. Okay, so 2, 3, 3, 4 like this. Okay, so this sorting is happening like this way in the recursive call. Okay, if you will explore this, your algorithm actually doing your task like this. Okay, the call maybe flow will be work like this. So your call will be happen to first call will be run like this, and then it will move to this, and so this part will happen first. Okay, then it will return back, but then this part will be explore. Okay, so till the at this point, this part will be performed and it will return back. After that, merging will happen for this part. Okay, then this second call will be happen. So this is just a way to how you can understand your recursive call. So these are the two
Sir,
call basically. Huh.
excuse me, sir. Sir, can you explain the merging part again? On each step, is it requiring n? Is it running n times on each merging step?
No, no, no. So here our size is reduced now. Here our size is reduced at every time. So it will not take the total n steps.
So basically, after each list have only one element, we are comparing two lists and putting them in order. So on the first level, we are where we have added 3, 4, 7, 8, and we have done that. So we have done 4 comparisons, right?
For comparison. So here
So the loop
because
will
size
run
is
4
different.
times.
Yes. So here merge sort is not okay shown here. So okay, how the merging is happen? Let me explain that part also. So okay, so we will also cover the merge here in this way. Just give me a First thing, understand how merge operation is happen in order of n time. So let's take two lists, okay, L1 and L2. And suppose you have the element. So questions may be also asked on this merge process from the merge sort. So like 1, 3, 5, 7, you have. Generally, we always get the similar size of list, okay, because we are dividing our array into two half at every time. Okay, so there is a chance you will get like 3 and 4 size, but most of the time you will get an equal size for the input because of the implementation way. Okay, so like the other size you have two like 4, 6, 8. Okay, this input both are sorted. So merge will always receive a 2 sorted list. I'm explaining this with the help of 4 size, but that will start with the one single element in the merge sort actually to explain better. So how merge actually works? So merge actually works. We have two lists. Indexing is like 0, 1, 2, 3, 0, 1, 2, 3, both list. We set our two pointer. So I equal to 0, j equal to 0. Okay, we maintain a1 another final list L3. Okay, so either you can perform append operation. Okay, so in L3, so initially this is empty. So I am considering this. Okay, now we start the comparison process to merge this. So we start if our L1, okay, so L1 of I is less than equal to, we can also take the equal to condition, L2 of j. Okay, so j variable we are taking. If this condition is true, we are comparing the element of first position element of the both list. If this condition is true, we will append our this element. Which one is the smaller element? Okay, we will append this element to a final list. Okay, so like we can write like this: L3 dot append and L1I. Correct. So this is, I think, understandable. If a smaller element, we are comparing both element. If and then we will pass our smaller element to the final list. So that should come first in the sorted list. So once this L1 element is moved to the final sorted list, we will increment our I variable, not j. Okay, I plus 1, because that element we have passed to the final sorted list. We will not compare that element again to other elements. So in this case, this is the one condition. Else condition for this situation, that is the reverse situation. If this is smaller, okay, else condition is only if this is smaller, L2 side is smaller. So in that case, you will pass L3 dot append L2 j. Okay, and you will increment j counter, j plus 1. So this is the one condition. and these conditions will be run inside one while loop, because we have the element. So what condition we will take for the while loop? So we have the size for L1, we have the size for L2. So we can take the condition like, suppose M is representing the length of L1. Okay, suppose this is 4. N is representing the length of L2. So this is also 4. So in while condition, we can run a condition like, if I is less than equal to 4. Okay, and j is less than equal to 4. This loop is running. Okay, inside this loop condition, we will run these conditions. It is clear? Now just run a dry run. Okay, so 1 and 2, which one is the smaller? This one. This will append here. Okay, now your I will move to this position. Okay, now 3 and 2, compare these two elements. Which one is the smaller? 2. Correct? This side. So this is second condition is true. So j, this part will be append in this output list, and j will be moved to the next element. J will come by this. Okay, and next is this 3 and 4. Which one is the smaller? 3. So this 3 will move here, and now your I will move to the next element. Okay, now 5 and 4, which one is the smaller? 4. So 4 will move to so this is moved. Now j will increment to next index. Now which 5 and 6, which one is the smaller? So 5. So 5 will append in this. I will be reached at the last index. Okay, so still I is 3. 3 is less than 4. Okay, so now 3 is less than this 6. Okay, so 3 is less than 6. So no, 7. Sorry, 7 is 6 is smaller. So 6 will move, and j will move to this. Okay, now I and j. So 7 is smaller than 8. Yes. So 7 will reach, but I will increment one more time. Okay, so I will become a 4. Correct? So in this case, this loop is now terminated. This condition is become false. The loop will terminate. After this while loop, we will also check if any element is remaining in any list which is not included. We will pass all that element into directly. So here you can see this is element is still not passed. So after this while completion, we will check if our I is still less than or equal to our size. So then if any list is for checking fulfilling this condition, we will pass all the remaining element of that list. So this remaining is 8, so that we will pass. Okay, so in this case, you can see we are getting a final sorted list in this process. And this is how many comparison is where we happen. So 4 is here, 4 is here. Okay, so how many comparison is happened in this process? Total near to 8. Correct. So first we compare this 1 to 2, then 1 to this. No, so 1 to 2, and then 3 to 2, and then 3 to 4, and then 4 to 5. So if you count this, this is similar to your 2n minus 1 approx. This is the worst situation actually of the comparison. So this is also a important things. When you will see the implementation, you can conclude that what is the worst case possibility and what is the best case possibility of the comparison. But this loop will learn order of n time actually. Okay, order of n, because we have the n by 2 element in the 2 list. So we are just combining this. Or if you consider n equal to 4, n equal to 4, still complexity will be considered as it. So here comparison is 2n. Okay, 2n. But we remove the constant, order of n. Okay. So this process is order of n time complexity process. So I hope this is clear. If you see the algorithm, let's open the algorithm for this. So you will see same thing we are doing. Way of implementation may be different, but the prof or I have.
Sir, where was the login, sir? The login part.
Login part that I'll explain here. I am just explaining now that merge sort. Yeah, merge sort this one. Okay, you see this. So this process you can see First we are receiving A and B in this algorithm. So length of M and N we have taken. We have taken this I and J from 0 0 index initially set, and C final output list we have taken empty list. Okay. And first we are checking this condition when we have the element in both lists to compare. Okay, while I is less than M, J is less than M. We are performing this comparison. Okay. And based on that, we are passing our element to the C list. But maybe so during this comparison process, there is a chance that one list is completely passed to the sorted. Suppose, okay, there is one more situation you can see. Yes, suppose our input sorted list is coming like this: 1, 2, 3, 4, and this side like 8, 10, 20, 30. Okay, this L1, this L2. Okay, and you start the process I here and J here. So what will happen in this case? This element will compare with this first, okay, and that this will be passed to the final sort. This will increment to this, okay. Now 2 is smaller than 8, so in this case again 2 will pass. Then I will increment it. I equal to 3. This 3 is still smaller than 8. 3 will pass, and then I will reach here. Okay, so 4 is still smaller than 8, so 4 will pass. Now I is cross the boundary. Okay, so index 5. Now this first while loop will break. Okay, but this still is remaining. Okay, so we have to check after checking the while loop with the both I is less than M or J is less than N. If our loop is break, then we will check if any element is remaining into the another list or not. So we will check for both L1 or L2. So here you can see all elements are remaining, which is not inserted into the final list because our J is initially at the 0th index. So in that case, so now this is type of best case situation. Suppose if you have 4 element, now comparison is only done 4. Okay, but after that, these all elements just pass as it is into this list. Okay, 8, just move to the next 10, then 20, then 30. Okay, so this is not a comparison, this is just a inserting. Comparison is happening with 1 and 8, 2 and 8, 3 and 8, 4 and 8, like this. So this type of situation can come. So implementation covers this also by the second case. Okay, so you can see first condition we have checked when both have the element for compare. If any list is completed, so then we are checking if still I is less than M, then we will append all the element from this list. If J is less than N, then we will append all the remaining element. Any condition is satisfied, so all remaining element will come into the final sorted list. So this is the merge algorithm. Okay, so this is taking order of n time. Now this part is merge sort. Okay, now just I am explaining this. You can see this is the overall length. We are checking this is the base case for this. Okay, this is the base case, and this is a recursive call, merge sort of the half input, first half, and merge sort on the second half. This is the second recursive call on the second half elements. And after that, we are merging both. Okay, we are merging both into a one sorted list. So this is the merge call. So this merge call, you can see this in the recursive call. We are calling this merge function. So this is taking order of n time. So now we can write a recurrence relation for this. So Tn, okay, Tn is the overall call. So just see the merge sort call, merge sort function. This function, just see how many times we call the recursive function. Anyone?
Log on times.
How many? No. Just tell me how many calls are there inside this body.
2, sir.
2 calls.
One call.
No, there are 2 calls.
Two.
You can see this one and this one. 2 calls are there in this person. Okay. First call is on the first half of the element. Second call is on the second half of the element of the list. So that means input is we reduce the half actually here. Okay. So both call we are passing the half elements. So we will write this as there are 2 recursive call, 2. Okay. And both call is input is passing n by 2, or we can write like this: Tn, there is one call n by 2 size, another call n by 2 size. Apart from this, what are the remaining part complexity of the code? Actually, what is the complexity for the remaining part actually? So this part you can see this is a constant operation, but this merge function is calling inside this. This is order of n, correct? So the maximum part is order of n, other than the call actually. So this order of n, this is the additional time. So we will write this as a order of n, or you can write just like a n. This is also time. So we can write like as it n equal to 2t n by 2 plus n. So this become a recurrence relation for this type of algorithm where multiple calls are there. Now this can be solved. I think there are multiple methods are there, master methods are there. Okay, and one recurrence tree methods is also there that will also discuss in week 8. But I'm giving the idea of that. So how that recurrence tree you can easily calculate the complexity. So initially, I am just drawing the structure of call. Okay, and we will also note down the additional steps. So Tn is the first call. Okay, now from this call we are calling 2 times again. So this is become a 2 call. Okay, so T n by 2 and T n by 2, correct? Additionally, we have the n steps. Okay, so this is the merging steps we are taking. That is taking so that merging will happen at this step. So that is taking n step. Okay, this I have written this one. 2 calls are there and then n steps are there. Now this is a new call.
Sir, this n step means that both the splitting and joining, sir.
Yes, this is the merging time actually. When we are receiving 2 n by 2 n by 2 size, we are merging that process. It is taking order of n time.
Okay, sir.
Okay, now our size is n by 2. Okay, so this is a new problem. This is another new problem. These two separate problems actually. Here n by 2 elements, n by 2 elements. This will again divide like this. So 2t. So same thing. T n by 4. Okay, n by 4, because just divide by this n by 2 by 2. So it become n by 4 and T n by 4. 2 call. Okay, another recursive call. And with this, how many additional time is required to compare this? To merge this actually. To merge this n by 4 and this is also n by 4. It will take n by 2 step. Okay, same thing happen here. T n by 4. This is the one call T n by 4. And to merging this, we have n by 2 steps. Because size is input size is n by 4 or n by 4. When we will compare, so it will take n by 2 steps. Okay, now again this will expand further. Okay, so now n by 8 like this. Okay, so additional step will be at this merging process will be n by 4 here. Okay, n by 4 here, n by 4 here. So this is the additional merging step actually, and the call is actually n by 8. This is Tn. So I will not expand further. So this is called as a recurrence tree. Okay, this is become like a tree structure. So Tn by 8. Okay, now just check the level wise time. Okay, so this time we got the n operation. At this level, how many total operations are there? So this n by 2 and this n by 2. N by 2 plus n by 2, n. Correct? Here, n by 4 plus n by 4 plus n by 4 plus n by 4.
Yes.
4 into n by 4, n.
N.
Each level you are getting n steps. Now this become a n by 8. Then if you will perform n by 8 times, you will get n again. Okay. So now you can also see every time we are dividing n by n to n by 2, then n by 4, then n by 8 like this. Okay, so this is just like a dividing by 2 every time, like a binary search things. So how many levels will be there to reach the base case T1? Initially, suppose you have n equal to 1024, so it become a 512 here, become a 256 here, so like 128 here till 1. So how many steps you are performing. Log n. It is correct.
Yes, sir.
Okay. So total number of levels are log n levels. Okay. Log n at log n steps we will reach this base case when we will expand
Sir,
this. Huh.
sir, for the SCT, if we don't want to give it again, do we have to still fill the Google form with no, or we can just leave it without filling?
Okay, I'm not sure about this SCT exam. You can check with the support.
Okay, thank you, sir.
Okay. Okay. So total number of levels are log n. Each levels you have n steps. So how many steps will total?
Log n.
N
N
into log
times.
n. No? This is the simple calculation. Total log n levels are there. Each levels you have n operation. So total number of operation are n log n. So this become a n log n complexity. So this is the simple one. When we are getting divide into actual equal half, so then we are getting this type of complexity, simple n log n. We can conclude this. We will also see a difference when our operations of each level will increase maybe. Okay, it may be increased to n, and then next step it will become a 2n, next step it will become 4n, or like 8n, like this. So in that case we will calculate the complexity in different way. If our number of operations are reducing, then we have the different formula to calculate. Okay, right now I'm just explaining this. For this is used for the merge sort and quick sort also it will use. So but we will see the detailed things about this recurrence tree to solve the different type of condition. Okay, that is recurrence tree. So right now for the so same things, how we can get 2 to the power n situation. Suppose if you have a recursive call fn where inside the body you are calling like this, return fn minus 1 plus fn minus 1 2 times, like this type of some base case is there, and you are calling this type of recursive call. Okay, fn initial call, base case is there, then this is the recursive part where you are calling 2 times this n minus 1. Okay, so how it will expand actually, fn next call is fn n minus 1 and fn n minus 1. Okay, it will expand f n minus 2, n minus 2, fn minus 2, fn minus 2. Okay, so here the value is decreasing 1 only at each steps, but this is expanding 2 times. Okay, so now the number of operation, if you just consider as a remaining operations are or 1 only. Okay, so how many operation will be performed? So this step 2 to the power 0 you can consider equal to 1 operation. Okay, here plus 1 plus 1. Okay, so 2 to the power 1 equal to 2. This is the next level, n minus 2. So here 2 to the power 2, 4 value you will get. So this will expand till f1. Okay, so this is the, so how many levels will be there to reach this total n level? Okay, on second level you are getting calculation from 2 to the power 2. So this you can consider as a level number, 2 to the power 2, 4. When you will reach at the last level, okay, that nth level, so that at that time total how many calls will be there? So that is actually 2 to the power n. So this is the highest order of, so 2 to the power n plus 2 to the power n minus 1, like this. So we will consider only the highest order. So that will become this complexity 2 to the power n of this type of code. Okay, so you will get this type of condition also for some code. So so this is the way to calculate the complexity. I have given the idea. Yeah.
Is this merge sort merges in place in the
No,
list?
this merge sort is not the not perform the in place. Okay, we are using additional list here. You can see C. This
Okay,
C
sir.
list is the additional list. We are using additional space. So this is not called as a in place sorting. We are not performing the sorting on the same input list. We are using additional list for this. Okay, so now this is the way of the complexity. Other than this part, I think let's quickly discuss the algorithms. So if you have any specific doubt of any algorithm, you can ask. So other than this, first is searching. Let's discuss the searching. So first searching, you know about the naive search, that is called as a linear search. So I think this is very clear. Searching, we are just running a linear loop, and we are simply comparing each element with our searching element. Okay, so you can see this implementation. We have some input list like 3, 1, 5, 4, 2, 8, like this, and we are running a length of this loop for I in range of length of L, and we are comparing our element with the each index. So this is the one index like this, each comparison. So this is taking total number of what is the size of list. That is the worst case situation. So order of n time. But as I mentioned that best case. So for this is 1 because our searching element may be at the first position. Worst case, this is the order of n if our element is not exist or exist at the last place. Average case, because the average case total count will become as n/2. Okay, because our element may at this first position, this second position. So how many comparison is required for the first case? 1. For second case 2, then 3, then 4, like this till n. If you will add all these and divide it by n, so that will come like as a n/2. But we generally not take the constant part, so we are representing order of n for this also. Average case. Okay, so this is the linear search. I think this is clear. This is very naive approach. If anyone have any doubt, so please stop me and ask. Okay, binary search, this is the main algorithm actually. So binary search is the improved version for the searching, but there is one prerequisite for this. What is the prerequisite for this?
It should be sorted.
So our input list should be sorted. Then we can apply this type of binary search. So this is the prerequisite for this. So now this is idea of this algorithm is because we are considering that our input list is sorted. So we can figure out. So like 1, 3, 5, 8, 9, 10, 11, 12, 13, like this type of order is there. Okay, sorted order. Now if we are searching any element, so idea is simply just always check the middle element first. Okay, so if suppose if you are searching like 8, this time we will always search the middle position element, and then we will compare which side our searching element will come. Okay, so if you are searching 8 and you are just checking the middle element like 11, okay, so 8 will come because this order is sorted. So this 8 should be come into the left side, not it cannot come to the right side because this is sorted. Okay. So we can conclude this information by checking the middle element, and we can discard half of the complete part without checking, because our 8 element will not come into the right side. Just remove all the part to checking. So half of the element removed in the one step. Now this is the searching area because 11 is not meshed. So this is the next searching area. Okay. Again, we will follow the same process. We will figure out the middle element in this remaining part. Okay. Suppose you have 5, so you are getting this 5. Now again, 8 is greater than 5, not matched, but greater than. Then you can discard this complete left part. Now the remaining part is only this 8 and 10. So again, just check if what is the starting index and last index and divide by 2. So dividing process, you can see how you are checking initial index, first index and last index, and below division by 2. You are getting middle index and you are checking that element. So in this way, you will reach your searching element in log n steps, because every time you are removing half of the size. So that we have already seen. If we reduce our input size to the half at every time, so maximum log n steps is required to reach at the reach at the base case or one final element. Okay. So in this case, this is the basic approach for this. So you can see we are setting low and to 0, high to last index initially. After that, we are running a while loop when low is less than equal to high, because we will repeat this process multiple times when we will reach at the one single element. So that should be the some terminate condition for the inside the while loop. Every time we are calculating the middle element by adding this low plus high equal to flow division by 2, and we are simply comparing. If our element is less than, our searching element is greater than, set our low to the mid plus 1. If our searching element is smaller than, set your high to the mid minus 1. And otherwise return mid. If our element is matched, return mid. If this process is completed without getting the answer, then finally return false. That means element is not exist. So this is the idea, okay, the algorithm of the binary search. So here multiple implementation you can do. So this is one implementation, just we are using iteration inside the while loop, and this is the log n complexities for that. One interesting thing is here you can also see the recursive implementation. So that is not a, this is just like a different type of implementation. So every time when we are dividing into the half, we are calling the recursive function same. So this is just another way to write the same time of task using the recursion. If you are very good in the recursion concept, you can write the same task in the recursive way. But don't try to learn each type of code. If you're comfortable with the iterative methods, just use that, okay? Because both are doing the same thing. But here, one important thing is, so there's one more implementation. This one, okay? And this is discussed in the prof lecture actually. So maybe this is conceptually this is also correct. But if we are using this implementation to achieve log n time complexity in the practical scenario or in some editor or some other code editor, this code may be fail. Why this will fail? Because here we are using slicing operation in these two steps. Okay, this is the Python facility. It provides very short things and we can directly use this. Conceptually, we are doing the right task. We are dividing our list into the half. But internally, it's performed some operation. This, what is the meaning of this slicing actually when we are passing into a recursive function? So this L slicing mid, what it is generating actually? It is so L list, we have the L list, input list. This is the input list. When we are passing into the function using the slicing, it is creating a new object actually, new list. Okay, it is passing with the, in the new call, it is passing with the same name L, but this is the different object, not the same input object. So this maybe if you will check the ID for this, suppose the ID will be different for the new list actually, for the new. And what happening by this slicing operation? So 0 to mid minus 1, these elements are copying to this new list one by one. Okay, so n by 2 elements are copying to the new created list internally. So it is taking n by 2 steps actually. So if you are copying n by 2 elements into a new list, that will take n by 2 steps. That is actually a order of n complexity. Okay, suppose if n is 1 lakh, that means 50,000 operation will perform. So that is approximately similar to a linear time operation. So that is order of n operation internally. So our basic overall goal to achieve the log n steps, but there is a one single operation internally happen with the order of n complexity. So practically it will fail on the portal or in some place, because this operation is now a order of n operation. So it will become equivalent to your linear search time complexity. So because of that we mentioned that just do not use this type of slicing when you are getting less than, when your goal is to achieve the less than n complexity. Do not use this slicing. Okay, so use the different implementation in your practical scenario. Conceptually, this is correct. Many places you will find this type of approach in books or when you will see the Python documents. So, but do not use this practically in any question. Okay, so this is binary search. Now sorting algorithm. So we have mentioned merge sort, okay, and now the two sorting algorithm, selection sort. So do not, again I am seeing, do not see the code directly here. Just understand what is the idea. Actually, we use the selection sort. Okay, so selection sort, we are getting some input list and a sorted list, and like 3, 5, 1, 4, 2, 9, like this. Okay, so what is the basic idea is simply to solve this algorithm, you should also have the idea how you can find the minimum element. So this is a sub problem for this, how you can find a minimum element in your input list. So I think everyone can solve this part, finding the minimum or finding the maximum element in your list.
Yes, sir.
Okay, this is the simple steps. Just consider that the first element is the smallest, then compare each element and figure out that if you find smaller than this, just change your smallest element. So this is the finding the smallest element in your list. This is the one sub part you should know. Then just repeat the same process for each position. Okay, so now first position, from this point to last element, figure out that which one is the smallest element. Okay, from the current selected position to the last element. So this one is the smallest element. Okay, now selected position is this, and you find that this index is the one is the smallest element position. And after finding this, swap this, these two elements, current position and smallest element position. Now you will get a element like 1, 5, 3, 4, 2, 9. Now just move to the next position, because this part becomes sorted. Just skip this, move to the second position, and only check the remaining part, because this is the still unsorted part. Just consider this as input, and finding this for this position to the last element, find the smallest element again. Same steps you are repeating, but the current position is now this. Okay, so what is the smallest element? This one, second. So same step you are doing with each position. Now you can see we figure out this. This is the smallest element and this is the current position. So just swap this. Okay, so 1, 2, 3, 4, 5, 9. Now this part is become sorted. Each iteration, each pass, till that point, your list will become sorted. Now next position is this. Do the same process again. From this position to the last position, repeat the same, finding the minimum. So what is the minimum? The same minimum. Okay, so perform the swapping, so it will not affect. So 1, 2, 3, 3. So all process will be repeat again. So the same thing will happen with this position. So this will also not change. This will also not change. This will also not change. But your algorithm will work work the task. Okay, so that will compare each element to check the next minimum. So this is the overall idea of the selection sort algorithm. Okay, so now you can just, if you understand this idea, then just try to write the code for this. So then this become a selection sort implementation. Someone raised the hand. No. Okay, so now you can see now how you can write the implementation for this. That is up to you. One of the implementation is given here. So you can see what we are doing. We are figuring out if this is just a base case. So if our size is less than 1, we will directly return the answer. Otherwise, we are doing the same thing. You can see this I is just pointing to a position, and this part is looking the smallest element from this position to the last element. And after that, we are swapping the current position to the smallest element. So this part. This we will repeat for the each position, and we will return the same list again. So this will perform your selection sort. So in this case, to understand the complexity for this case, so this algorithm doing the full process doesn't matter what type of order you are giving to the in this input list. If you are giving still sorted list 1, 2, 3, 4, 5, 6, still algorithm is doing the same full process. Okay, it will check this condition and it will search. It will compare each element and then figure out that this is the smallest element and will swap this. Same thing happened with the second element. Okay, so it is performing all complete tasks, doesn't matter what input is giving. So how many steps are required for the first position? So for first position, it will compare the all remaining elements. Okay, so we can consider that it is performing n minus 1 steps for the first position. For second position, one element is now removed. Second position, n minus 2 steps. For third position, n minus 3 steps. In this way till 1. So if you will add this series, you will get total step n into n plus 1 divided by 2 like this step. Or when you will multiply this, you will get a n square order. Okay. So overall complexity will become n square. And this n square complexity will remain in all type of cases. Either your list is already sorted, reverse, or anything. So your task will be done completely. Okay. So this is selection sort. Any doubt in selection sort? Also, this is in place selection, in place sorting. Okay, this is in place because we are performing swapping in the same input list and we are performing the sorting with the help of this. We're not using any additional list for this. Yeah, any query in this selection sort?
No, sir.
Okay. One more important point about selection sort, stable. Generally, this is also one property of the sorting algorithm. Your sorting algorithm is stable sorting algorithm or not? What is the meaning of this? So stable meaning is, suppose if you have two elements with the same value, okay, in the input. So like 3, 4, 2, 3 like this. Okay, this is the input list. You have two elements, 3 and 3. So this is the input. In the output sorted list, you will get a 2, 3, 3, and 4. This is the output sorted of the sorting algorithm. So are we changing the order of the same value in the output sorted list or not? So is there any guarantee that our order of the same element will not change? Then our algorithm will called be as a stable sort, otherwise not. So just consider that this is just like a first A and this is the second. This is the order of, okay, so this A is coming first, B is coming second in the input list. So in final output, A, this first 3 should be the same A and this should be the B. Okay, if this is the guaranteed by our sorting algorithm, then our algorithm is stable sort, otherwise not. So stable, this selection sort is not stable. So okay, so we can understand this by some counter example. So like suppose we have one okay, like okay, 1 second, 3 okay, 2, 3, 1. Suppose this is the input. Okay, so this is the A and this is the B. According to the selection sort, what will happen? So you can see this is the first position and we will find out the smallest element in this. Now this is the smallest, okay, S, and this is I suppose. So now swapping will happen in this. When swapping will happen, this 3 will move to the last position. So this will become a 1, 2, 3, and 3. And this is now a B and this is a A. Now in the remaining steps, nothing will be changed. So you can see order is changed. Okay, so this is proof that selection sort is not stable because here swapping is happen maybe between any index. So that may change the order of the same elements. So selection sort is not a stable sort algorithm. And next algorithm is.
I think if they're next to each other, then I don't think there is a problem with stability, right? in the selection sort I'm talking about. So there were a couple of elements between the 3 at position 0 versus 3 at position 4. So if they were back to back, like if they were at element
So
0 and 1.
sometimes, yes, sometimes it will not change. Your order will not change. I have given the counter example where it is changed.
No, I'm saying,
I'm not
but
saying
if
that.
I'm saying if they are, so my counter example to that, I would probably say if they are back to back in back to back positions, right? Then it's unlikely that they will be swept, right? I mean, the comparison would return false, right? I mean, is 3 less than 3? It would be false.
So what counter example you are taking? Can you tell me? Suppose 1
I'm
3
yeah,
like.
yeah. If it is 1 3 and then again a 3 and then some element and then some element. So I'm saying, so if it's going to compare, so after if 3 compares to 3, then it won't swap, right? The
It won't
condition
swap.
won't.
Yeah, it won't swap.
Yeah. So that's what I'm saying. So I'm saying if they're back to back, then it is unlikely that they're going to swap. So if they are somewhere far apart, couple of elements apart, then they might
But
swap.
okay, so but there is a chance here also. Okay, suppose if I'm taking 2 here.
Okay, then so then yeah, you're right. Yeah, I can see the
Correct.
point. Okay.
So
Yeah.
this is the position. Actually, this will change the condition.
Okay, got it.
Okay. So now next is last is insertion sort for today. So what is the basic idea of insertion sort algorithm? So here actually we suppose we have the list 3 2 1 4 6 8 5 like any inputs another list. Okay, so idea of the basic here is we consider as a first single element as a sorted element, because here we are starting from the single element. If we have the single element, as I already mentioned in the merge sort also, we consider as a sorted element. Now we start the process from the second position element. Okay, so this person, and we just compare with the previous element, and we will figure out that where this should actually insert it to maintain the sorted order. Okay, so how we can check? So we have the only one sorted element, and now we are just inserting 2 in this. So we will simply compare the previous just element, and we will see it is in the correct order or not. If it's not correct, we will swap these 2 positions. Then we will check again to the next previous element if we have. So we will repeat this process. So that means we are just selecting one element and we are inserting that element into a previous sorted part. Okay, I'm taking one example like 1 5 8 10. This is suppose we have the sorted part. Okay, and one new element is coming like 3. Okay, so how we can insert that into a correct position to maintain our sorted order? So what we can do, we can simply compare with the last element. So this 10 is greater than this. So what we can do, we can just shift this to a 1 position to the right, because this 3 is smaller than this. Okay, now next thing, we will compare again to the 8. Okay, still 8 is 3 is smaller than 8. Then we will shift our 8 to 1 position to the right, and again we will compare to the 3 and 5. So 5 is still greater than, we will shift this to the right. Okay, now 3 and 1. Now this is correct order. So this place is become empty, and we will just insert this 3 here. Okay, so either you can do by this shifting process, or either you can do by the swapping process. Okay, so 3 and 10 compare. Suppose just append this 3 at the last position and then perform the swapping. Okay, just 10 will become here, 3 will become here. Again compare to the adjacent previous one. Then again swapping. In this way, your inserted element will inserted into a correct position. So 1 3 5 8 10. Now this becomes a sorted order again. Okay, so the same idea we are using here. We are checking for the each element, and we are inserting that element to a previous sorted part. Okay, so always previous part will be the sorted order, because we are starting from the single element, so that is actually sorted. Now we are checking for the 2, and we are just inserting that into a correct position in the previous sorted part. So only single element is there. So 2 and 3. So to make this sorted, so we will swap this. So it will become a 2 3. Okay, Now the remaining part is next is this one. Okay. Now one we will take and we will check where this should be inserted to maintain the sorted order in the previous sorted order. So one we will pick and we will compare with 3. Okay, so 3 is greater than. Then we will swap this. Okay, then we will again compare to the previous element. Yeah, still it is greater than. Then we will again swap this. So now we will get 1, 2, 3. Okay. Now we will pick this 4. So now 4 is actually greater than 3. After because this part is sorted, if our element is greater than to the last element, so no need to compare to the previous element because all previous elements are smaller than this. So we will compare this 4 is greater than 3. Okay, this is in correct order. So just keep this as it is. Okay, without comparing with the remaining one. Now 6. Okay, 6 is still greater than 4. No comparison, only one comparison is required. And this is maintaining the sorted order. Now 8 is also maintaining. Okay, now 5 comes. So 5 is now smaller than 8. Okay, now we will swap this and then we will compare with 6. Yeah, still 6 is greater than. Now that will stop at this place. Okay, so 4 is smaller than this. So till that point, now 5 will insert it at this position. So 1, 2, 3, 4, 5, 6, 8. So this process we are performing with the insertion sort. We are starting with the second element and we are just looking into a previous sorted order where that element should be inserted to maintain the sorted order. So this is the basic idea of the insertion sort, and we can implement this in different way, either using the swapping or maybe shifting process. So so we have discussed this swapping process in our approach, but shifting is also you can do. So swapping, same things you can see, because so this things is the base case, and here this is the loop. Okay, this loop is running I equal to n, j equal to I we are setting. Okay, so this you can start either from one index. Okay, so this implementation may take some additional steps or something, but you can also improve this. So this is starting from 0 index, but I think that is not required. You can start with the 1 index. So that will also work. So each time what we are doing, so j is the current position I. Okay, and from we are starting from j and we are comparing j with the previous element j minus 1. Okay, if this condition is true, and also how much time we will repeat this process if our condition is true, because till the 0th index. Okay, if our j is greater than 0, otherwise we have to stop, because before 0 there is no element. So that we will stop the process. So because of that two condition we are maintaining, our j should be greater than 0 or our j should be less than to the previous element. Then we will repeat this while loop. Okay, and if this both conditions become true, then we will swap the element, both j and j minus 1 we will swap, and we will shift our j to previous one position previous. Okay, to compare to the next previous element. So these steps are maintaining the insertion process into a sorted part. And each time one element will be inserted into a sorted, the previous part becoming sorted. So this is the basic idea of the insertion sort. Now this is also a in-place sorting algorithm, and it is a stable also. Why this is stable? Because here actually shifting is happening. If you are getting like 4, 3, 1, 2, 3. So here you are maintaining the sorted order from the first element like this. Okay, so this is 4, and when we will insert, so this 3 is coming first, so this will insert first into the correct order. So when the second 3 will come, so that will only check the previous bigger element. It will not swap the element position with when we will reach at the this same element again. Okay, so if any similar element is already inserted into the sorted order, so we will not change the position. We will not compare to this, or we will not swap with this element. Okay, so that element can come from the higher side to and reach to the same element, but then it will not move further. It will stop the process here. So in this, because of that, this order will not be changed of the same element in this process. And about the complexity of this. Okay, so here the best case, and this depends on the insertion. So here the best case. So insertion sort behaves is different with the best case and worst case. So because of this while loop, as you see that if our order is like this, 1, 2, 3, 4, 5, 6, okay, or already sorted order. So what will happen? So we will run a outer loop for each position from this, okay. But every time we will simply compare to the previous element sorted part with the previous first element only, and our element is greater than to this. So that one step our while loop will terminate. Okay, so 2 to 1 stop. Okay, so now this is already order 1 and 2. Now we will check for 3. So 3 will only compare to 2, and then we will stop our while process, okay, without repeating again. So 3, then 4 we will compare, only comparison will happen with 3, one comparison. So each time for each outer loop I, one step is performing. Okay, so that means this loop is running internally and it is stopping at one step every time. So in this case, if our order is already sorted or either all elements are same, like this is also a case. In this case also, your step will be run order of n time. Okay, outer loop will run and internally one operation is performing. So either your input is sorted or same element. Okay, so in this case, this type of case, complexity will be order of n. But if your order is different, like reverse order 6, 5, 4, 3, 2, 1, so this is like a worst case situation when the all comparison. So this element will be compared with 1. Next step it will compare with 2. Third element will compare with 3 to move to the correct position. So in this way, n minus 1. So this will become a same type of scenario of selection sort, n plus 1 by 2, total n square. So insertion sort takes order of n square in worst case, but order of n in best case. Average case also is order of n square. So this is the basic idea. You can implement this algorithm in your style or in your way. Okay, so this idea should be very clear to understand the concept or to solve the question. So this is the all content, sorting algorithm and complexity. I hope this is clear. Just see the lecture also again if you have not watched and solve all the question. I think all will be clear if you will solve.
Sir, can you please suggest some books? Can you please suggest some books for these type of codes and
Okay.
log?
There are actually very standard books. We have also shared the links for that books, but that books are very much deep actually. Okay, so we have the Core Man, a very popular book. We have Core Man.
Codeman.
Thomas H. Corman. No, Corman. Cormen. You can search the book Corman for the data structure and algorithm. Another book we have John Kleinberg and Eva Tardos, these writers. And we have given the link for these books. We have already have these books soft copy
Can you
on the
please
Discourse.
please post the name in the chat box?
1 second. What
name of the books?
So I'm sending the Discourse link. I hope you using the Discourse.
Yes, sir.
Discourse. So this is one first post now. So you can see this first post where the topic is books. This link that is have the soft copy of books of the all. Corman is there, Dasgupta is there, Kleinberg is there. Okay, I'm sending the link of this in chat. But these books are very depth. Okay, so I created the these notes also. So if you want to learn in very depth, if you have enough time, so you can also follow these books.
So right now I can go with Corman, right?
I'm not sure how much time you can give to learn the Corman book because this is approx. Let me check. Please, I have the physical book also for this. That is very big actually. But yeah, topic wise you can just see. So total 1300 pages there. So you can just search the topic, what topic you want to learn, just see that content only. Okay. Otherwise it will give too much, it will take too much time if you want to just study in the depth. But yeah, we will definitely prefer book once you complete this course, to just learn in the deeper way.
Okay.
After this course. Okay, so this is all about the Week-2 content. So just solve all these assignments. Then I think this time we have included more questions in your assignments to understand concept clearly. Okay, any other query, anyone?
Thank you very much.
Okay, thanks.
Thank you, sir.
Yeah.
Thank you. Good night.
Okay.
Sir.
Good
Thank you,
night.
sir.
Bye.
Thank you, sir.
Okay.
Thank you.
Someone is saying, okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay, bye.